Each year, the world produces only about 300,000 tons of titanium. Yet to obtain it, vast amounts of ore, nearly 10 times as much, must be processed through extremely intricate procedures, making titanium one of the most valuable materials on Earth. So what makes a metal that is almost invisible in everyday life so powerful? The journey begins deep underground, where titanium remains hidden within layers of ilmenite and rutile that few ever notice. But once extracted, it quickly enters a chain of metallurgical technologies unlike anything seen before, paving the way for titanium to become a foundational material behind many major military technological breakthroughs in the latter half of the 20th century. Today, join Agriculture Insight as we explore the journey of transforming titanium from raw ore into a pure metal through some of the most advanced metallurgical processes in the world. Titanium can be considered a super metal of the modern era, about 45% lighter than steel, yet offering exceptional strength, highly resistant to seawater corrosion, and capable of lasting for decades. For this reason, it is used in extreme applications such as the supersonic reconnaissance aircraft Lockheed SR-71 Blackbird and the hulls of nuclear submarines like the Alpha-class submarine, built from solid titanium. It can even remain inside the human body for long periods without rejection, becoming dental implants, cranial plates, and joint replacements. However, titanium is not always the optimal choice. Its high extraction and processing costs mean many industries still rely on aluminum or steel. Even Apple Inc., after turning titanium into a premium signature on the iPhone 15 and iPhone 16, is rumored to return to aluminum frames on the iPhone 17 for economic and environmental reasons, a shift that has sparked debate among iPhone users worldwide. So what about you? Would you choose a premium titanium frame or a lighter, more practical aluminum one? To understand why titanium has become such a remarkable material, we must return to its origin, the journey of extraction from deep within the earth. The mining process begins with identifying deposits of ilmenite and rutile, titanium oxide-rich minerals hidden within ancient sand formations in regions such as Panjihua and Hainan. For coastal placer deposits, high-capacity hydraulic pumping systems use high-pressure water jets to strip away thick layers of sand in a short time, simultaneously creating a mineral slurry. After preliminary separation, the titanium-bearing slurry settles in collection areas. Here, large-scale excavators continuously scoop and gather the mixture of mud, water, and sand rich in titanium-bearing minerals. This material is then fed into pumping systems and transported through long pipelines to processing plants for further separation and refinement. Meanwhile, at titanium deposits located deep inland, the process shifts to open-pit mining using heavy machinery, combined with drilling and blasting, to break through overburden and ore bodies. After each blast, large excavators collect the fragmented material, and ultra-heavy trucks transport to 400 tons per load to stockpiles. However, the biggest common factor between both methods is the enormous demand for resources, especially water. A single titanium mine can consume up to 5,000 cubic meters per day, equivalent to the needs of an entire small town, turning titanium extraction into a constant balancing act between advanced materials and environmental responsibility. After leaving the mine, raw titanium ore is first crushed and screened to achieve the appropriate particle size, then passed through a series of gravity separation processes, such as spiral concentrators and shaking tables, to gradually separate lighter sand from heavier mineral particles. The material is then processed through magnetic and electrostatic separation systems to remove iron, silica, and other unwanted minerals, progressively increasing the titanium concentration. Notably, from 1 ton of initial placer sand, engineers typically recover only about 30 to 80 kilograms of titanium concentrate, while the remaining material is returned for environmental rehabilitation. This low recovery rate, combined with the multi-stage processing required, is why titanium, despite being abundant in nature, remains relatively rare and highly valuable in industrial applications. Unlike steel, which can be melted directly, titanium becomes brittle like glass when exposed to oxygen at high temperatures. As a result, instead of simply smelting the ore, engineers must first convert titanium into an intermediate fluid form before extracting the pure metal. Inside sealed reactors operating at nearly 1,000 degrees Celsius, the concentrated ore reacts with chlorine and carbon to produce titanium tetrachloride, a clear liquid that fumes upon contact with air. Through multiple stages of distillation, impurities such as iron and manganese are removed to parts per million levels, making the compound pure enough for the next step. It is then reacted with magnesium in sealed reactors for 48 to 72 hours, during which titanium gradually crystallizes along the reactor walls. The result is not a shiny metal ingot, but a gray, porous mass known as titanium sponge, resembling a honeycomb structure and representing the first metallic form of titanium on Earth. But titanium sponge still cannot be used for aircraft or submarines, as it must first be purified to an extremely high level. The raw honeycomb-like mass is crushed, thoroughly washed to remove magnesium chloride salts, and then vacuum dried for many hours. Even a few grams of residual salt can ruin the entire downstream refining batch, making this a true aerospace-grade cleaning step before titanium enters its final melting stage. After purification, titanium electrodes are fed into a VAR, vacuum arc remelting furnace, where the metal is remelted under a pressure of around 10 megapascals at, far lower than the atmospheric pressure at the summit of Mount Everest. Here, an electric arc with a current of up to 30,000 to 40,000 amperes melts the titanium, allowing it to resolidify layer by layer inside a continuously cooled copper mold. However, to meet aerospace standards, this process is typically repeated for 2 to 3 consecutive cycles, each pass further removing residual oxygen, nitrogen, and microscopic structural imperfections until the entire metal ingot reaches the uniformity required for extreme operating conditions. Immediately after being removed from the furnace, the refined titanium ingot remains red hot, with surface temperatures exceeding 1,000 degrees Celsius. In this state, the metal enters the hot working range, where titanium becomes more ductile and easier to deform while still retaining its inherent strength, an ideal condition for initial forming operations. A massive industrial robotic arm firmly grips the multi-ton ingot and swiftly transfers it into a hydraulic press before the temperature drops below the required threshold. Inside the press, large pistons gradually descend with immense force, each compression producing a thunder-like impact. Under this pressure, the titanium ingot begins to transform visibly. From a rough cylindrical block, it is progressively flattened, elongated, and reshaped into a more uniform geometry. This process typically occurs over multiple forging cycles, combined with repositioning and rotating the workpiece to ensure the force is evenly distributed throughout the entire metal mass. More important than its external shape, this hot forging process profoundly transforms the internal structure of titanium. Under high temperature and immense pressure, residual microscopic pores from casting are gradually eliminated, significantly increasing the material's density. At the same time, the internal crystal grains are realigned and elongated in the direction of deformation, forming a finer, more compact grain structure, key factors that give titanium its high mechanical strength, load-bearing capacity, and resistance to cracking. This stage also demands extremely precise control of parameters, such as temperature, pressing speed, and the number of deformation cycles. as even minor deviations can affect the final material properties. It is at this moment that titanium ceases to be a raw cast ingot and begins its transformation into a high-performance engineering material, ready for the most demanding applications in aerospace, biomedical, and modern industry. After titanium is rolled into standard billets, the journey to transform it into true engineering components only begins. First, the billet surfaces are cut and ground to remove the oxide layer formed during metallurgical processing. Next, the titanium blocks are transferred to industrial lathes and milling machines for rough shaping under a continuous flow of coolant, as titanium retains heat intensely and can damage cutting tools within minutes if not handled properly. The most critical stage then takes place on CNC machines, where high-speed cutting tools move along precisely programmed paths down to thousandths of a millimeter, enabling turning, milling, drilling, and engraving of titanium into complex components, transforming a notoriously difficult-to-machine metal into parts ready for the most demanding high-precision engineering systems. For titanium bars, once rolling and machining are completed to the required technical standards, they are not transported individually, but bundled into engineering packs consisting of dozens to hundreds of bars, depending on their size and intended application. These bundles are then tightly secured with high-strength steel straps and wrapped with specialized plastic or oil-treated paper to prevent moisture exposure and protect against even the smallest surface scratches during transportation over thousands of kilometers. Chile is currently the world's largest copper producer, accounting for around 25 to 30% of global output, followed by Peru and China, forming a strategically important global supply chain. However, as demand continues to surge driven by electric vehicles and renewable energy, while new deposits are becoming increasingly difficult to access, many experts warn of a potential supply shortage in the future. Compared to other metals, copper has a lower electrical conductivity than silver, but it offers far greater cost efficiency. It also performs better and remains more stable than aluminum over long-term use, and is significantly more effective at conducting electricity than metals such as steel. This balance between conductivity, durability, and cost is what makes copper the optimal choice and a foundational material in most modern electrical systems. Behind every copper-based product lies a vast industrial process, operating on a massive scale. This journey begins with the extraction of copper ore from either open-pit mines or deep underground deposits. In open-pit mining, the process begins with stripping away the overburden, the layers of soil and rock covering the copper ore body beneath. This material is not simply discarded. It is carefully managed and transported to designated waste dump areas to ensure slope stability and overall mine safety. Once the ore body is exposed, geologists and engineers conduct detailed geological surveys to determine rock structure, hardness, and the distribution of mineral deposits. Based on this data, a precise drilling pattern is designed, where hole depth, angle, and spacing are carefully calculated to maximize fragmentation efficiency while minimizing risks such as ground instability or impacts on surrounding areas. Industrial explosives are then loaded into each drilled hole and detonated using millisecond delay sequencing. This controlled, multi-stage blasting creates a series of timed explosions that break the rock into manageable sizes, reducing the need for extensive primary crushing in later stages and improving overall processing efficiency. Immediately afterward, large hydraulic excavators move in to collect the broken ore and load it onto heavy haul trucks. Each truck can carry hundreds of tons per trip, and operates continuously along internal mine roads designed in spiral patterns, allowing stable transport from the pit floor up to the surface. The entire system, from stripping and drilling to blasting and hauling, operates as a tightly integrated chain, where each stage is synchronized to maintain a steady flow of ore for the downstream processing stages. If open-pit mining exposes the surface, underground mining moves in the opposite direction, descending deep into the earth to reach ore bodies located at great depths. From a main shaft, horizontal and vertical tunnels are excavated through layers of rock, forming a complex, maze-like network. Within this environment, specialized drilling machines continue boring into the ore body, followed by the use of explosives to break the rock in confined spaces, requiring far higher precision and control compared to open-pit operations. Once fragmented, the ore is not transported by large haul trucks as on the surface. Instead, it is brought to the surface using conveyor belts, rail carts, or vertical hoisting shaft systems. At the same time, the entire underground network must be continuously ventilated to supply fresh oxygen and remove toxic gases, along with rock reinforcement measures to ensure worker safety. It is these harsh conditions and confined spaces that make underground mining far more complex and costly, yet it becomes the only viable option when copper deposits lie deep beneath the earth. After leaving the mining site, copper ore is transported by conveyor belts or haul trucks to large-scale processing plants. Here, the entire operation runs almost continuously, with automated systems tightly controlling each stage of the process. Inside the plant, the copper ore passes through a multi-stage crushing system to reduce its size in a controlled manner. Initially, primary crushers break large rock fragments into smaller pieces, which are then fed into secondary and tertiary crushers to produce finer particles. The ore is often mixed with water to form a slurry, which improves transport and processing efficiency while helping to fully liberate the copper-bearing minerals for subsequent separation. Particle size is strictly controlled, as even minor deviations can significantly affect metal recovery efficiency. After fine grinding, the ore is sent to the flotation stage, a critical step for separating copper from the surrounding waste rock. At this stage, the slurry is mixed with water and chemical reagents, while air is injected to generate fine bubbles. Copper-bearing particles attach to these bubbles and rise to the surface, while impurities sink to the bottom. The resulting froth layer, enriched with copper, is then collected to produce a higher-grade concentrate, ready for the next stages of smelting and refining. Next, the copper concentrate is fed into large industrial furnaces, typically reverberatory furnaces or modern smelting systems, where temperatures can exceed 1000 degrees Celsius to separate the metal from unwanted components. In this environment, continuous chemical reactions take place, producing molten copper and slag, with the latter carrying impurities that are removed from the process. The result is crude copper, not yet highly pure but ready for the next stage of refining. The molten copper from the smelting furnace is continuously poured into large molds, typically through automated casting systems, to form thick plates known as anodes. Each plate can weigh several hundred kilograms and is cooled with water to maintain its shape before being lifted out by overhead cranes. Although already in metallic form, these anodes still contain impurities, such as sulfur, iron, and other metals, so they cannot be used directly and instead serve as raw electrodes for the next stage of refining. The anode plates are suspended in electrolytic tanks filled with an acidic solution, alternating with cathodes made of pure metal. When an electric current is applied, copper from the anode gradually dissolves into the solution and deposits onto the cathode as pure metal, while the anode itself is consumed, its surface becoming rough, porous, and noticeably thinner over time. Insoluble impurities fall to the bottom, forming anode slime, which may even contain precious metals such as gold or silver. After several days, the cathodes are removed, now coated with copper of about 99.99% purity, ready for the next stages of processing. After electrolytic refining, pure cathode copper is melted and continuously cast into long copper rods. The molten metal is poured through cooling molds, solidifying into bright, uniform rods with a standard diameter and consistent quality. Depending on the production line, these rods may be cut into sections for storage or kept in continuous form for direct transfer to the wire drawing stage. The most critical step is wire drawing, in which copper rods are pulled through a series of dies with progressively smaller openings to reduce diameter and elongate the metal. This process occurs in multiple stages, from coarse wire to very fine strands, increasing mechanical strength, but also causing the copper to harden due to friction. To counter this, annealing is performed intermittently to soften the material and restore ductility, preventing breakage during subsequent drawing stages. Once the desired size is achieved, the wire is cooled, cleaned, and tested for electrical conductivity and tensile strength, then wound into large coils, ready for use in the production of electrical wiring, industrial cables, and electronic components. Copper is not only used as a conductive material in industry, but also plays a role in high-precision manufacturing processes, notably in forming the metal jacket for bullets in engineering and defense applications. The process begins with material selection. Copper is preferred for its superior strength and excellent corrosion resistance, allowing the projectile to withstand high pressure and temperature during firing. The raw copper is then fed into rolling systems where it is transformed into thin metal sheets with thickness precisely controlled down to fine tolerances. Next, the copper sheets are punched into circular blanks using high-precision stamping machines, ensuring uniform dimensions with minimal tolerances. The blanks are then cleaned and may undergo light annealing to improve ductility, preparing them for subsequent forming processes. This stage is critical, as initial precision directly affects the quality of the final product. After being cut into circular blanks, the copper pieces are fed into a deep drawing press to form cups. A cup-shaped structure with a closed base and thin walls. Under high pressure, the material is stretched and reshaped, creating the initial form of the metal jacket. During this process, thickness and dimensions are tightly controlled to ensure uniformity, while lubrication or annealing may be applied to reduce friction and prevent cracking. This is an important intermediate step before further elongation and final finishing. Following the cupping stage, the next step is multi-stage drawing. The cups are passed through a series of dies with progressively smaller diameters to elongate the body, thin the walls, and gradually increase height. This process occurs continuously across multiple stages, with pressing force and speed tightly controlled to ensure uniform wall thickness and to minimize unwanted deformation. Throughout the process, the surface is lubricated to reduce friction, and intermediate annealing may be applied to restore ductility and prevent cracking caused by work hardening. As a result, the component gradually achieves the required dimensions, shape, and structural stability before moving on to the subsequent forming stages. Once the cups have been sufficiently elongated, they move to the necking stage. Here, the upper section is pressed through dies to gradually reduce its diameter, forming the characteristic tapered neck with precise dimensional control. This step defines the final geometry and ensures proper fit and stability for the subsequent finishing processes. After the metal casing has been fully formed, the core is inserted inside through a process known as core seating. At this stage, the core is pressed tightly into the casing under high compressive force, ensuring precise positioning and stable contact between the two materials, while minimizing any gaps or misalignment during assembly. This process requires strict control over pressing force, speed, and dimensional tolerances, as even a slight deviation can lead to off-center alignment or structural deformation. In addition, the weight and placement of the core are closely monitored to ensure balance, uniformity, and overall stability of the product before it moves on to the final forming stage. Finally, once the core has been perfectly secured and all parameters meet absolute standards, the entire component enters the final inspection stage, where even micrometer-level deviations are examined with extreme precision. This is not merely a quality check, but a moment of quality affirmation, ensuring the structure achieves near-perfect durability, concentricity, and stability. Any minor deviation, no matter how small, is immediately corrected to preserve complete consistency across all units within the production batch. When every standard has been fully satisfied, the component is officially ready for the final finishing process, closing the manufacturing journey with a crucial transformation from a precise technical assembly into a fully completed product of the highest refinement. The true turning point of the modern American oil industry came in 1901, when the Spindletop oil well in Texas suddenly erupted, shooting oil more than 45 meters into the air and producing up to 100,000 barrels per day. This event sparked the Texas oil boom and marked the beginning of the explosive growth of the oil and gas industry in the United States. Today, the United States is the largest oil producer in the world, with production reaching nearly 13 million barrels per day. Among all states, Texas plays the central role, producing over 40% of the nation's total oil output. Some even say that if Texas were an independent country, it would rank among the world's top oil-producing nations. However, the United States is also the largest consumer of oil on the planet, despite having only about 4% of the world's population, a relatively small share compared to its enormous energy consumption. As a result, fuel prices in the US are a highly sensitive economic issue. When fuel prices rise, transportation and goods become more expensive, which directly affects inflation and can even influence elections. To protect its energy security, the United States established the Strategic Petroleum Reserve, the largest emergency oil reserve in the world. It can store more than 700 million barrels of oil in massive underground salt caverns. This system was created after the 1973 oil crisis, ensuring that if global oil supplies are disrupted, the US economy would still have enough energy to keep running. For this reason, oil is not just a fuel, it is also a strategic resource closely tied to the economic and political power of the United States. Now let's travel back hundreds of millions of years to see how the black gold that powers our world today was truly formed. Around 100 to 300 million years ago, ancient oceans were filled with countless algae and microscopic marine organisms. When these organisms died, their remains sank to the seafloor and were gradually buried beneath layers of mud and sediment. Over time, the immense heat and pressure deep within the earth transformed this organic material into hydrocarbons, the fundamental components of crude oil. These hydrocarbons then migrated through porous rock layers and became trapped in geological formations known as oil traps, deep beneath the ground or ocean floor. After accumulating for hundreds of millions of years, they formed vast oil reservoirs that today require drilling as deep as 10 to 12 kilometers into the earth to reach. But how do humans manage to find oil reservoirs buried kilometers beneath the Earth's surface? The answer begins with the stage known as oil exploration. Long before any drilling rig appears, geologists must first see deep underground using seismic surveys. Specialized vessels send powerful sound waves down into the ground or the ocean floor. When these waves encounter different rock layers, they bounce back and are recorded by thousands of sensors. Using this data, computers construct detailed 3D maps of geological structures located 2 to 5 kilometers beneath the surface. Even so, searching for oil remains a high-risk endeavor. On average, only about 1 out of 10 exploration sites ultimately contains oil in quantities large enough to be commercially viable. But if a promising oil trap is discovered, the reward can be enormous. Such a reservoir may hold hundreds of millions of tons of crude oil, a massive energy resource capable of powering entire economies for decades. Most offshore drilling rigs are constructed in large shipyards and industrial ports, where massive steel frameworks are welded together into modules. A single rig can weigh 10,000 to 30,000 tons, equipped with a towering drill derrick, heavy cranes, power generators, living quarters, and even a helicopter landing pad. Essentially, a small industrial city at sea. Once completed, the entire structure is transported by heavy lift barges or specialized vessels to the oil field, often located 100 to 300 kilometers offshore. At the site, engineers lower the steel jacket structure to the seabed. Giant steel piles, sometimes over 100 meters long, are driven deep into the seabed sediments and secured with concrete to create a stable foundation. After that, the deck of the drilling platform, weighing thousands of tons, is carefully lifted and placed onto the jacket using super heavy cranes with remarkable precision. Only when this steel city is fully installed amid the waves of the open ocean can drilling operations finally begin, opening the path to oil reservoirs hidden kilometers beneath the Earth's surface. Once the drilling platform is firmly anchored in the ocean, the real work begins: drilling the oil well. From the top of the derrick, which can rise dozens of meters high, steel pipes about 9 to 10 meters long are connected one by one to form a massive drill string that slowly penetrates deep into the earth. At the tip is an ultra-hard alloy drill bit that rotates continuously, crushing ancient rock layers located 2 to 5 kilometers beneath the surface. Throughout the process, a special fluid known as drilling mud is pumped constantly down the well. It acts like the lifeblood of the drilling system, cooling the drill bit, stabilizing the well walls, and carrying rock cuttings from deep underground back to the surface for engineers to analyze. Drilling a single well can take several weeks to several months, and offshore projects can cost 50 to 100 million USD per well. Today, many wells are not drilled only vertically, but also horizontally, for an additional 1 to 3 kilometers, allowing access to more oil-bearing layers within the same reservoir. But at these depths, geological pressure can exceed 10,000 psi, hundreds of times greater than atmospheric pressure. For that reason, every meter of drilling must be carefully controlled, because even a small mistake can trigger a dangerous oil blowout. When the drill bit finally penetrates the oil-bearing rock layer, the well enters its most critical stage: oil production. Inside the well, engineers install production tubing to channel the fluid from several kilometers underground up to the surface. In many newly discovered reservoirs, the natural pressure within the oil-bearing formation can be strong enough to push the oil upward on its own, like a massive underground spring suddenly released. However, this natural flow usually lasts only during the early stage of production. As reservoir pressure gradually declines, mechanical pumps or electric submersible pumps (ESP) are installed to maintain the flow. A modern industrial pump can lift 15,000 to 20,000 barrels of oil per day, operating continuously several kilometers beneath the Earth's surface. It's important to note that the fluid rising from the well is not pure oil. Instead, it is a mixture of crude oil, natural gas, water, and fine sand carried up from the surrounding rock layers. For this reason, at the drilling platform or nearby gathering station, the mixture is directed into high-pressure separators, where oil, gas, and water are separated into different streams. This is the first stage of processing before the crude oil is sent through pipelines and continues its journey to oil refineries. When the fluid from an oil well reaches the surface, it is not pure oil but a mixture of crude oil, natural gas, water, and fine sand. In many oil fields, the actual oil may make up only 60 to 70% of the mixture, while the rest consists of water and gas. For this reason, the mixture must first be sent into high-pressure separators installed directly on the drilling platform. Inside these separators, the pressure is reduced so that the components can separate naturally based on density. Natural gas, being the lightest, rises to the top and is collected to be compressed into gas pipelines or re-injected into the reservoir to maintain pressure. Crude oil forms the middle layer and is directed into temporary storage tanks. Meanwhile, water and sand, which are heavier, settle at the bottom and are removed for separate treatment. After this initial separation, the crude oil becomes stable enough for transportation. It is then pumped into subsea pipelines stretching hundreds of kilometers or transferred to oil tankers capable of carrying millions of barrels, beginning its journey to refineries on land where it will be transformed into gasoline, diesel, and many other petroleum products. Not all oil reserves lie beneath the ocean. On land, oil extraction takes place in a more familiar setting but remains just as complex. Once a well reaches the oil-bearing layer, crude oil is brought to the surface through production tubing. In the early stage, natural pressure in the reservoir may push the oil upward on its own. But as the pressure declines, mechanical pumping systems begin to take over, the most recognizable being the pump jack, the machine with a rhythmic metal arm often seen in onshore oil fields. Each pump jack works like a giant underground syringe, drawing oil from depths of about 1 to 3 kilometers below the surface. A typical onshore well can produce 20 to 300 barrels of oil per day, depending on the size and richness of the reservoir. In major oil regions, such as the Permian Basin in Texas, where more than 7,000 wells are currently operating, thousands of pump jacks move up and down day and night, forming vast fields of pumps stretching across the landscape. The fluid brought to the surface is still a mixture of oil, gas, and water, so it must first be separated at nearby gathering stations before the crude oil is sent through pipelines or tanker trucks to refineries. From these slowly moving machines scattered across dry fields, a resource formed over hundreds of millions of years begins its journey into the modern global economy. After leaving the oil fields, crude oil is transported to oil refineries, facilities where one of the most complex industrial processes in the world takes place. A large refinery can process 300,000 to 600,000 barrels of crude oil per day, operating continuously around the clock. The most important step in this process is fractional distillation. First, crude oil is heated to about 350 to 370 degrees Celsius, turning it into vapor before it enters a distillation tower that can rise dozens of meters high. As the vapor moves upward inside the tower, different hydrocarbon compounds condense at different heights depending on their boiling points. The heaviest fractions, such as asphalt and lubricating oils, condense near the bottom. Above them are diesel, followed by kerosene and jet fuel, while gasoline condenses closer to the upper levels. At the very top of the tower are light gases such as propane and butane. However, the products obtained at this stage are still not fully ready for use. Many hydrocarbon molecules remain too large or do not yet meet fuel standards. They must undergo further processes such as cracking, which breaks large molecules into smaller ones, reforming, which improves fuel quality, and blending, where different components are mixed to meet precise technical specifications. Through this chain of processes, a single 159-liter barrel of crude oil can be transformed into gasoline, diesel, jet fuel, and thousands of petrochemical products that power the modern global economy. During the extraction of petroleum, crude oil is often produced together with large amounts of natural gas. When oil companies do not yet have the infrastructure to capture or transport this gas, they carry out a process known as gas flaring, which involves burning the excess gas on tall flare stacks at the oil field. This practice helps reduce pressure in the well and ensures safety by preventing the buildup of highly flammable gases. However, gas flaring is controversial because it releases carbon dioxide and other greenhouse gases into the atmosphere, while also wasting a valuable energy resource that could otherwise be used to generate electricity or fuel. As a result, in recent years, many countries and oil companies have been working to reduce gas flaring by capturing and utilizing the gas instead of burning it. To transform chaotic piles of collected plastic bottles into a consistent material stream, recycling facilities rely on a preliminary sorting stage where human labor and technology work closely together. Although 7 major plastic types exist, each marked by a recycling symbol, only PET and HDPE are commonly recycled into new products at scale. Therefore, the entire system is designed to preserve these 2 plastics while removing unsuitable materials as early as possible. The process begins when mixed plastic waste enters a massive rotating steel drum, perforated with rows of holes. As tons of bottles and packaging tumble inside, dirt, sand, and small debris fall through the openings, while larger plastic items continue moving forward. This step separates materials by size and prepares them for more precise sorting downstream. Next, conveyor belts carry plastics through manual sorting lines. Workers stationed along both sides quickly remove contaminants such as metal cans, plastic bags, and cardboard. At the same time, automated cutting blades detach caps and labels, often made from different plastics. Magnetic sensors extract small metal fragments like staples or leftover can lids. After this combined screening, the material stream becomes uniform, consisting of PET bottle bodies that are cleaner, purer, and ready to enter the next phase of the recycling journey. After sorting, rigid plastic bottles are fed into a shredding chamber where hundreds of alloy steel blades spin at extreme speed, producing a sharp, piercing noise that echoes through the factory. In moments, each bottle is ripped into countless uniform fragments only a few inches long, small enough to slide along the conveyor like a stream of glittering plastic sand under bright lights. The sheer power of these machines is astonishing. Each hour, they can process up to 3,000 pounds of plastic, quickly transforming mountains of bottles into tidy flakes within minutes. Shredding does more than reduce size. Finely chopped plastic melts far faster inside the extrusion furnace, saving up to 40% of energy compared with melting whole bottles. As a result, the entire production line runs faster while significantly lowering operating costs, creating a strong foundation for the next stage of high-tech sorting. This efficiency makes large-scale plastic recycling faster, cleaner, and more economically sustainable worldwide today. From these tiny fragments, optical technology and artificial intelligence handle the most delicate sorting stage of the entire process. A network of high-speed cameras scans each piece, analyzing color and surface structure within milliseconds. When the system detects clear PET, blue PE, white PE, HDPE, or foreign materials such as wood, ceramic, or glass, a burst of compressed air is instantly triggered, blowing that fragment out of the main material stream. The accuracy is astonishing. Each air jet targets a single plastic piece weighing less than 1,000th of an ounce, without disturbing neighboring fragments. On average, an optical sorting machine can process more than 10,000 pieces per second, with over 95% accuracy, equivalent to the output of hundreds of workers operating continuously without rest. Every second, tens of thousands of particles are separated precisely, forming streams ready for next stage. From the initial state of chaos, the material fragments are now pure enough to enter the pelletizing stage. After sorting, plastic flakes are fed into an extrusion system, where temperatures rise beyond 520 degrees. Under this intense heat, each fragment melts and blends into a thick plastic flow, moving forward like a stream of artificial lava. Inside the machine, a massive screw rotates continuously, mixing the molten material while steadily pushing it ahead. As the plastic travels along the length of the screw, pressure gradually increases, forcing the melt forward. When the material reaches the desired viscosity, it is pushed through ultrafine metal screens that trap the final impurities. At this stage, the molten plastic is cut into countless tiny pellets and immediately cooled with water to solidify their shape. Uniform in size, smooth-surfaced, they sparkle like gems. From uniform PE pellets, the manufacturing journey moves into a defined stage. Preform production, the foundation on which the final shape of the product is created. Inside the factory, material that has passed quality inspection is fed into a heating system, where temperatures rise to around 480 degrees, softening the plastic and preparing it to flow into molds. The result is a short component shaped like a test tube, known as a preform. Each preform has a thick body, while the neck is already formed with threads for a cap. Designed to withstand high temperatures and mechanical pressure, preforms maintain stability throughout transportation and subsequent processing. The advantages of preforms are not limited to technical performance. Their compact size optimizes storage and logistics, allowing millions of units to be transported efficiently without occupying excessive space. For this reason, many facilities specialize solely in preform production, supplying beverage companies, where they are blown into finished bottles closer to points of consumption. When the preforms are ready, they enter a decisive stage, blow molding, where they take on the true form of a plastic bottle. The preforms are fed into a heating system, warmed just enough for the plastic to become flexible while maintaining structural stability. Immediately afterward, high-pressure compressed air is blown in through the neck, causing the plastic walls to expand evenly and press tightly against the metal mold surface, precisely engineered to the desired shape. A 1.5-liter bottle preform, initially only about 10 to 12 centimeters long, can stretch 4 to 5 times its original height during the blowing process. This technique is considered one of the most precise and highly automated stages in PET bottle manufacturing. Each system can produce thousands of bottles within seconds, with deviations controlled to minimal levels. Wall thickness, cap thread accuracy, concentricity, and surface gloss are continuously monitored by sensors and computer software. The result is a lightweight bottle that remains strong enough to hold carbonated beverages, resist leakage, and maintain its shape under pressure. Beyond meeting technical standards, this process offers remarkable flexibility. Bottle volume, body curves, label placement, and even embossed logos can be customized to meet brand requirements. It is here that a simple plastic preform is transformed into a complete PET bottle, ready for cooling and packaging. Immediately after leaving the blow mold, the bottle surface remains at very high temperature, making the plastic walls soft and easily deformed if not treated at once. For this reason, production lines guide bottles into an instant cooling system. Streams of cold air or circulating water stabilize the bottle structure. This rapid cooling process allows the material to harden quickly and retain its original shape. Notably, in modern factories, cooling speed is calibrated with extreme precision. A newly formed PET bottle can reach a safe temperature in under 5 seconds. In addition, many systems recover heat released from bottles to warm water or air, saving energy and reducing operating costs. Once the plastic has fully solidified, the bottle gains mechanical strength needed for stacking, labeling, and withstanding impacts during transportation. Cooling time is calculated to avoid slowing production lines while ensuring clarity and rigidity. When the bottle body is fully stabilized, the journey continues with a rigorous inspection stage to ensure quality before the product reaches consumers. The inspection line is equipped with sensors, cameras, and high-precision measuring devices. Each product is scanned to detect cracks, air bubbles, or dimensional deviations. In addition, random samples undergo mechanical tests such as tension, compression, and impact to evaluate strength. For bottles intended for food and beverages, laboratories conduct chemical analysis to ensure no harmful residues remain. Only after passing this entire strict sequence of checks is the product allowed to move to the next stage. Approved bottles are grouped into large batches, stacked on pallets, and wrapped in protective film. Automated robotic palletizing systems arrange thousands of bottles, containers, or plastic products neatly and accurately. Each batch is labeled with traceability codes, ensuring full transparency from recycled raw materials to finished goods. Products ship from warehouses, completing a circular journey.